All right, welcome to ECE 203 lecture 15. Today we're going to continue our discussions from last time about filters. Today we're going to talk about LTI systems, or linear time invariant systems. And then we're also going to go through an example of how we can do discrete time convolution. Okay? So before we get started with that, I just want to go through two important discrete time signals. So we saw this impulse last lecture, right? We looked at the impulse response of an FIR filter. But I just want to remind you guys what an impulse is and how we're going to define that particular discrete time signal in this class, okay? So we're going to use the symbol delta of n, and that's just going to take on the value of 1 for this time index. Think of this as a time index of n equals 0, okay? And it's going to be 0 everywhere else. So intuitively, right, that's what a discrete time impulse would be, right? Impulse just means, you know, something that has very concentrated energy, and that's what this signal is. Okay, and there's a plot of that drawn on the right here, right? You can see for all values of n except n equals 0, the impulse takes on the value of +1. All right, so the second signal that's important that we'll use for a number of different reasons is the unit step function, okay, sometimes called the Heaviside step function, and that's just denoted with a u, okay, so u of n, and that signal, that discrete time signal, takes on the value of 1 for all n greater than or equal to 0, and it's 0 any other time, for any n less than 0. That's just drawn on the right here, right? Just looks like a step function. So at 0, you can think of it as turning on, and it just stays on, and it has a value of 1, right? For any n greater than 0, greater than or equal to 0. So even at 0, it takes on the value of +1. But of course, at time n equals -1, it's just 0. All right, so we can build more complicated signals using these two particular signals, okay, using the impulse and the step function. All right, some examples are what I have written down here, this delta of n minus 2 plus 2 times delta of n. So if we think about the signal for a while, we'd see, okay, well, the first thing is that when n equals 0, we're going to get the value 2, right? Because the delta of 0 takes a value of 1, and that gets multiplied by 2. So that's really just this value, right? And then it's going to be 0 everywhere else except when this first delta turns on. And what time does this first delta turn on? It turns on when n equals 2, right? And the way to see that is then we'd have delta of 2 minus 2, which is delta of 0. And if we go back up to our definition, delta of 0 is 1, right? So when n equals -2, this signal also takes the value 1. And that guy's just plotted right here. So we can add up these kind of shifted versions of the delta function and create really any signal that we want. So another thing we can do is take the step function, right? And comes up in this example that I have here. You think of this first term, u of n, that just kind of turns on and stays on when n equals 0. Okay? So when n equals 0, I could write this out, get u of 0 minus u of 0 plus 2, right? So what would happen here? No, I'm actually noticing there's an error in this. So we can also build these signals, more complicated signals out of this this u of n function, this step function. I'm just realizing there's a minor typo here. I wanted to have was u of n minus 2, not u of n plus 2. Okay, so what does this signal do, this u of n minus u of n minus 2? Well, here's what it does. If we look at the value n equals 0, right, then this first term is just going to be u of 0. And then we get minus u of minus 2. Okay? And so this guy is on, so this takes on the value of 1, and then we have minus 0. Okay? So for the value 0, n equals 0, we get this guy, it turns on. And if we looked at n equals, just erase this quickly, if we looked at n equals 1, then we'd see essentially the same thing. It would still be on. This first term would be on, and this guy would not be on, so we just have 1 minus 0 again. So if we look at n equals 2, that's when it gets slightly more interesting. Then we have u of 2 minus u of 2 minus 2, which is 0. Okay? And these are both 1, so that's 1 minus 1. So the signal takes a value of 0 when n equals 2, and that's plotted right there. So for any n greater than or equal to 2, you'll see that same behavior. So it just goes on for time samples 0 and 1. Okay, so now let's kind of talk about the core material of today's lecture, and that's 3 key properties of filters. So again, when you're thinking about a filter, just think of this box H. This is going to be our filter, and we're inputting a signal x of n, and the box H somehow modifies or affects the signal in some way. You can think of it as changing a particular frequency component, or maybe totally knocking out a particular frequency component, and that's something we'll look at in more detail in coming lectures. Okay? So the first property we want to talk about is linearity. And we say a filter H is linear if the following is true. If we can take 2 signals, x1 and x2, and let's say the signals x1 and x2 have output, if we put them into the filter by themselves, y1 and y2, okay, if the relationship that's drawn there holds. So what does that mean? That means if I take the signal x1 and I scale it by some number a, and I take the signal x2, scale that by some number a, and then I add them together, okay, so that's a new signal. This thing here, which I'm drawing in parentheses, is a new signal. And if I take that new signal and put that into the filter, if I get out a signal that's just what I got out by putting x1 in alone, which is y1, times that same number a1, plus y2, which is what I got by putting in x2 alone, times a2. Okay, so if that relationship is true, then we say the filter is linear. Okay, so how would we check if a particular signal is linear or not? Well, let's actually kind of be a little explicit and go through this example of the 2-point moving average filter, which we have the input-output relationship is just written right here, right? The output is just a weighted sum of the current sample plus a weighted sum of the previous sample, the average of those two samples. That's why it's called the moving average filter. So if we wanted to check as to whether or not this particular signal is linear, this is what we would do. We'd first say, all right, I'm going to define a new signal, x of n, and I'm going to call that a1 times x1 of n plus a2 times x2 of n. Okay? And I'm going to input that into the filter. Okay? And so what would the output be? Well, it would be y of n, just going to, like 1/2. Now this whole signal gets input. Right? a1 x1 of n plus a2 x2 of n. Now we have to add on this second term here, plus 1/2, and we're inputting this signal x of n, which is defined right above, and that That gives us, again, A1 times x1 of n minus 1 plus A2 x of n minus 2. So it's pretty easy to see at this point that it is actually linear, but let's go through the steps and see now, just kind of doing a little algebra, how I can rewrite this output signal, y of n. All right, I can rewrite this as follows. I can just rewrite this as A1 times, I'm going to take this first term here, A1 times 1/2 x1 of n, and now I'm going to take this term from over here and say plus x1 of n minus 1. And now I have the remaining terms that I have to add. So it's just A2 times 1/2 x2 of n plus 1/2 x2 of n minus 1. All right, so what do we notice now by doing just all this algebra? Well, we just notice that if I were to input the signal x1 by itself, I would get this output that's underlined in blue. So we'll just call that y1 of n. And if I were to input the signal x2 by itself, I'd get this kind of second term. It's y2 of n. Okay, and each one of those are scaled by A1 and A2. And so it does indeed satisfy that property of being linear. Right? That if we weight and add together two inputs, the output we get is just the same as if we had taken the individual signals and input them by themselves and weighted the output. Now the signal y of n equals x squared of n is not linear. What's an easy way to see that? So to show that something's not linear, we could just pick a particular signal, a couple particular signals, and show that it doesn't satisfy the properties of linearity. So let's just pick two really easy signals. And say I choose x1 of n equals 2. Okay? For all n, so just constant signals, and x2 of n, let's just say x2 of n equals 3, right? So if I input these, if I input now x1 of n plus x2 of n into the squared system, what do I get out? Well, I should get 2 plus 3, right? So that should be, for any value of n, 2 plus 3, that should be 5. That quantity is squared, right? This is just 2 plus 3. So I get 5. Input 5 squared, the output should be 25. Right? So we'll call that y of n. Should be 25. But now if I had put these signals in individually, let's say I just put 2 in, what do I get out? Well, if I just put 2 in, I get y1 out, and I get y1, which is 2 squared, that's just 4. Likewise, when I input x2, I get 3 squared, which is 9. So that gives me an output of 9. And now if I take 4 plus 9, right, so saying, write this explicitly, y2 equals 9, it's 3 squared. If I take now y1 plus y2, it's 4 plus 9 should be 13. There's a problem, right? Because that does not equal 25. So we've just shown right there that the filter is nonlinear. Okay? And that's really easy to see with an example like squaring. That we're going to talk about is time invariance. And we say a filter or a system is time invariant if the following is true. If we can input the signal x of n, but now delayed by some amount n naught, so x of n minus n naught, we input that into the filter, that we just get a delayed version of the output. Okay? And that has to be true for all and not. So an example of two things that are, one that is time invariant and one that is not time invariant is, again, that moving average filter. Right? If we take the input-output relationship, y of n is 1/2 x of n plus 1/2 x of n minus 1. Equivalently, if we put in the signal x of n minus n naught into that system, what will we get in the output? Well, we get 1/2 x of n minus n naught, right, plus 1/2 x of n minus n naught minus 1, right? And that's exactly the same as if we were to just take the original signal, or the original output, excuse me, y of n, and delay that by n, some number of samples n naught. Right? So this is just equal to y of the original output delayed by n naught. Now, a case where that's not true is the second signal that's written here, where y of n equals n times x of n. In general, when you see n kind of outside of the argument of a particular signal, that means it's doing, the time is playing more importance than just delaying the signal, right? And so it's easy to pick an example where this is not true. Let's just pick the input x of n equals delta of n minus 5. So if we input x of n equals delta of n minus 5, the output that we should get is, it should be 0 everywhere, right? This signal, let me plot this. Here's 0. It's the axes. It's going to take on, we'll take on the value 0 here, 2, 3, 4, 5. It's going to take on the value 1. Okay, so if we input that signal into this filter y of n equals n times x of n, the output that we get should just be, well, it should again always be 0, except at time n equals 5. But now at time n equals 5, it scales this input. So here's x of n. The output, right, is going to be another signal. It's going to have 5 times the amplitude at that value. Right? Oops, drew it in the wrong spot. Okay, so it's going to have 5. This is going to have a value of 5 now. So how do we see that this is not time invariant? Well, if we put in the signal just delta of n, what would the output be? Well, you can check that the output would be, so if x of n equals delta of n, then the output is just going to be 0, right? Because y of n is going to be, the only time it's going to take on a non-zero value is when delta of n is non-zero, which is at time 0, and that would just give us, so we write this, y of 0 equals 0 times delta of 0, which is just 0. Okay? And so it does not satisfy this relationship that the output is just a time-shifted version of the input signal. Now the last property that I want to talk about is causality. And causality just means that the output of the filter only depends on past samples and present input samples. So a way to think of that is the output of the filter, say the output at time 5, only depends on the signal at time 5, at time 4, at time 3, ... all the way up to minus infinity. It means that the output does not depend on any time samples that haven't in some way arrived at the filter yet. Okay? So this one's really easy to see. And the way we would see this is, first we'd look at this and say, all right, the output at time n depends on the present sample of x of n, and then it depends on one previous sample of xn. So it's all samples that have already arrived. Now, the second signal depends on, the second filter depends on x of n plus 1, right? So say at time 0, the output at time 0, say n equals 0, depends on the input at time 1. So somehow, when you think of a practical system, this means that the sample may have not arrived at the filter yet. So we'd say that filter is non-causal. And it really implies that there's some dependence on time here, right? And if this is the case, we think of a filter operating on audio, of course the filter, if it's operating in real time, the output of the filter can't depend on my voice, something that I haven't spoken yet. Okay? And so in that way, causality only applies to signals that depend on time. If you think of an image, for example, causality doesn't really apply if you're trying to filter, say, a two-dimensional image. And non-causal filters can't be realized in practice unless you can accept some delay. All right? So if my output depends on a sample that hasn't arrived yet, I can just kind of wait and delay and not output anything, maybe delay the output for a while. And then I also want to say that we've looked at all these three definitions: linearity, time invariance, and causality, and these all apply to continuous time signals. We won't go through them, but the analysis would be exactly the same. Kind of the examples would be the exact same. The definitions would be the exact same, except with appropriate modification. We'd have t instead of n. All right, so that kind of wraps up the three important properties we're going to talk about today. But before we go on, I want to recall from last time the definition of an FIR filter, and that's written here. Okay? And the definition just says it's kind of a generalization of this moving average filter. Right? And we can see from this it's definitely causal, and it's also linear, and it's also time invariant. Right? So we say that such a system is now just linear time invariant, a linear time invariant system, or an LTI system. LTI stands for linear time invariant system. And it's easy to check. We really just did this in kind of the examples that we just went through, looking at the specific moving average filter, that FIR filters are linear and time invariant. All right. So again, a filter is LTI if it's linear and time invariant. And we might ask, well, why is that important? And the first reason is that a lot of signal processing tasks can be accomplished using LTI systems in practice. Okay? If you think back to the bass boost thing we did in lab, that was an LTI system. The second thing is we can describe any LTI system by how it affects signals at different frequencies. We'll see this in more detail, but what that means is if we have an LTI system and we can describe how it affects sinusoids of different frequencies, if I give you some function that says the sinusoid at this frequency is affected in this way, that completely characterizes the LTI system. And lastly, another way we can completely characterize the system is by its impulse response. And again, we saw this last time, but the fact, I'll just state this as a fact, any LTI system, any filter, the output can be written as the convolution, right? That's denoted by this star symbol here, the convolution between the impulse response of the filter and the input signal. So h of n convolved with x of n. That's, again, the signal does not mean multiplication. And we could write that out actually is in kind of the full definition of convolution is written here, right? Where h of n, again, is the response of the filter when we input a delta function in impulse. All right, so let's actually go on and try and calculate the output of a particular filter. All right, and the way we're going to do this is using convolution. All right, so the example we'll look at is something called the digital differentiator, and this is a type of high-pass filter. And so when I say high-pass filter, what does that mean? That means that high-frequency signals are able to pass through the filter. And you'll see what I mean, hopefully, within the next couple lectures, but let's now focus on the how we would calculate the output of this filter. So again, the input-output relationship, just kind of given, this is the definition of digital differentiator, okay? And it's just taking, it looks like the moving average filter, except we have a minus here, right? So it's taking the current input sample, multiplying it by 1/2, and then subtracting the previous input signal after it's multiplied by 1/2. So first, what is the impulse response of this? Well, it's really easy to just write out, and then we would just input every place we see xn here, we're going to replace that with a delta. So we get the following is the impulse response. H of n equals 1/2 delta of n minus 1/2 delta of n minus 1. And we can make a plot of that. Right? We kind of looked at these plots at the beginning of this lecture, and we'd see that the impulse response has 2 points. Right? It takes on the value 1/2 when n is 0, and it takes on the value minus 1/2 when n equals 1. Okay, so how would we calculate the output when the input is given by the plot drawn below? Okay, this plot looks kind of just like a little triangle. Well, the output is just, like I said, the impulse response convolved with the signal x of n. And we can write out that definition, this complicated sum over k equals minus infinity to infinity. The question is, how do we compute this? Right? So we have everything we need, right? We have h of n, we have x of n, and now we want to compute the convolution of h of n and x of n. How do we do this? We're going to step through this and kind of be as explicit as possible here. So here's what we would do. Again, now I've just kind of redrawn things at the top of the screen, convolving the signal h of n with the input x of n. These two signals are getting convolved together. So to compute the output y, let's just start with a particular value of n. So say n equals 0. Let's compute the output y of 0, the output at time 0. And if we look at this definition, the output at time 0, all we have to do is replace n by 0. So we put 0 in there. And then we have to multiply the signals together and sum over all values of k. Right? So that's precisely what we're going to do. Let's plot the signals before we multiply them together. So the first thing I want to do is plot h of k. And that's plotted right here. What does a plot of h of k look like? Well, it looks exactly like h of n, right? If I plot k on this axis. Just n is kind of a dummy variable, right? We think of it as the time index. Now plotting h of k, k is the time index. It looks exactly the same. But now we also want to plot x of 0 minus k. Remember, we're looking at the output at n equals 0. So we replaced n with a 0. So this is really just x of minus k, right? And so I'm plotting that here, down on this last plot on the screen. And you can see that plotting x of minus k, that actually kind of flips the horizontal axis, right? Because now we're not plotting just x of k, we're plotting x of minus k. So one way to think about this is like, say how do I get this value, say here, right? Well, I would say at this point k equals minus 2, right? This is minus 2. when k equals minus 2, I'd plug that into, say, x of minus k. So I'd have x of minus, parentheses, minus 2. And that just gives me the value of, so x of minus k, right, at the value minus 2 is x of minus 2. And that just equals the value of x of 2. Right? So we go all the way back up top, say what's the value at x of 2, and we just copy it down. It takes on the value 6 there, right? So that's amplitude of 6. So that's how this is sometimes termed the kind of flipping action in what some people say is a way of doing convolution, which is called flip and shift. But I'm just thinking of it as calculating x of minus k, right? And it does, the plot just looks like we flipped the plot of x. All right, so what next? What do we do next? Well, we're going to multiply these two signals together, h of k and x of minus k, and then we're going to sum them up over all values of k. All right? So I've got that written again on the same page. So we have these two signals, multiplying them together. Well, it's clear to me these are all zeros, right? So zeros times these guys, that's just going to give me zeros, right? And I'm plotting those down here, values of 0. The only place this is not going to be 0, this product is not going to be 0, is at the index k equals 0, right? And there it just takes on the value, this had a height 1/2, remember it was that impulse response, and this had the value 2, okay? So we get 1/2 times 2, and then zeros everywhere else. So now we're going to sum up 0 plus 0 plus 0 plus 1 plus 0 plus 0. So summing over all k just gives us 1. All right, so what do we conclude? Conclude that y of 0 is equal to 1. Let's move on to the next point. Let's calculate y of 1. How do we do that? Well, again, we can write out the definition of convolution. Y of 1, we'll see, right? We still just have h of k here, but now we have x of 1 minus k. So I'm going to plot, again, h of k. That looks exactly the same as before. But now I'm going to plot x of 1 minus k. And what did, instead, last time we had x of 0 minus k. Now if we look at x of 1 minus k, that has the effect of shifting the plot to the right. So it was flipped, and now we're shifting it to the right by 1 index. Okay, so now I'm going to multiply these two signals, h of k times x of k. And what does that do? Well, we just see that really there's only two non-zero values here. And the first one is going to be, should be plus 1/2 times 4. Okay? And that should give me a value of 2. And then the next one should be minus 1/2 times a value of 2, right? And that should give me minus 1. So now I'm going to add all of these guys up. Adding all of these up for all values of k. And what do I get? I get 0 plus 0 plus 0 plus 2 minus 1 plus 0 plus 0. So adding all these up, we just end up with y of 1 equals 1. How about y of 2? How would we figure out what y of 2 is? Well, again, h of k looks the same, but now we're plotting h of 2 minus k. So we've shifted this thing to the right by 2. We do the exact same thing. We'd multiply these two signals together and we'd add them all up. And we'd see that now the output with y of 2, again, we really just kind of get this guy multiplied by 1/2, this guy by minus 1/2, and we'd end up with 3 minus 2, and that just gives us an output value of 1. So we could keep going, right? We could evaluate y of 3. We see that's minus 1, evaluate y of 4, that again is minus 1, y of 5, one more minus 1, and then lastly y of 6, that would give us 0. So the total output signal after we did all that work would be y of n kind of drawn below. All right, that would be the output of the filter when input with that kind of triangle wave. So here's kind of one of the takeaway points is we can do this really quickly in MATLAB just by typing conv, okay? And conv of x comma h, where h and x are just two vectors containing the impulse response and the signal that we want to calculate the output of the filter of.